today we are going to start a new topic, which is transformation or functions of random variables, right. I think it's the shorter name is better, it is just functions of random variables. But you have to view these functions as transforming one random variable into another in the sense that, right. So, in the sense of this diagram. So, I have an input output relationship where the transformation is a simple function, it is not a complicated operation which transforms one sequence into another or one function of time into another function of time or any such thing. It is just a simple memoryless mapping between, right, one number and into another, which is basically the standard functional mapping that you studied way back when, right, 10th standard, 11th standard type material, that is all this is. So, what is this G? G is just in general is a function which takes you from R to R, and it is a deterministic function, right. So, G is deterministic. So, when we say deterministic, what do we mean? We mean it is fully known, i.e. it is specified or full or known, it is a known mapping, there is nothing random about G. Standard examples are squaring, linear transform like Ax plus b and so on, right. I do not have to elaborate that point, but what is interesting in this context is that its input is not just any real number x, but a random variable capital X, right. So, in other words, you are going to feed into G some, you are going to connect it to the output of a random experiment, right. The random experiment will throw at you some realization of some value of taken by capital X, and that will be transformed by G into Y. So, if you look at all the possible values you get out here as a result of this mapping, as a result of the random variable X going into this mapping G, so what do we get? So, can we call this output a random variable? It turns out yes, right. Because you are assuming that there is some statistical regularity or behavior, right, so some statistical description of what is coming in at the input, and that will transform into the statistical description of the output. So with the random variable X as input, we have Y equal to G of X, right. So this, the output random variable is simply this. So, if you take for example a simple picture, e.g. supposing I take some non-linear, now we are interested in, what are we interested in? Obviously we are interested in some non-linear function G, or just linear functions are not very, if you can't restrict yourself only to them, right. But let us assume that we have a monotonically increasing G, just for, so if you draw something like this, means it is, so right, so if I, okay, so what am I plotting here? I am plotting the domain of G along the x axis and the range or the values taken by G on the y axis. There is nothing random about this portion, right. This is just a specification, a graphical specification of G, right. And it turns out that, okay, so this is Y equal to G of X. It turns out that in general I do not need to worry about G for all of R, because in many cases, right, the omega x, the range of x is finite, is bounded. So there's you really need to specify this G only for omega x. So let me make that point clear first. And it is sufficient to specify G or G of x for x in omega x. You do not have to go around specifying it for every real number under the sun, right. So, i.e. you can write G as map going from omega x, and it of course the output could be any real number. We are not going to put any restriction on the output of G. So, this may be in general, but okay. So, this is one thing. So, here like, supposing if this is my omega x, let us say my random variable x is only going to take values in that interval. What does this mean on y? First of all, what are the set of values I will observe at the output? Obviously, I will in this particular with respect to this particular function, I am only going to observe this. If this is my omega x, let us say from x1 to x2, say, then I will only observe values in this case for monotonically increasing, or in this particular example, I will only observe omega y1 to y2. Of course, in general also, even if it is not monotonically increasing, you can still identify the range y1 to y2. Okay, this is easy to draw, so I am drawing it. So, omega x equal to, let us say, a closed interval x1, x2, does not matter, implies that omega y will be, in this case, g of x1 to g of x2, comma g of x2 for monotonically increasing g. This is just an, but this is a true statement in general, so I do not mind writing it down. If it were monotonically decreasing, you would put g of x2 before g of x1, it is okay, right. If it is going up and down, I am not going to draw all that because I do not have enough space on this board to do all the stuff that I normally do in ESB 127 or whatever, right. So, if it went up and down, you would of course, you would do the overlay the same thing, right. You just have to look at this x1 to x2 and apply to G and see what is the range of the output. So, that I will leave it to you to, anyway we will do enough examples, specific examples that will illustrate the point. So, there is no point in drawing pictures right now, right. So, this is the first important thing you have to understand, you have to see what is the range of the output random variable. In every situation, right, this is the first thing that you have to always determine, and we have done this so many times now that I am sounding like a broken record, repeating myself again and again, right. Any conditioning, any extra stuff you throw on it always changes the range, and that is, so the new range is what you have to calculate, right. So, this particular thing is very easy, but if it is going up and down, it is not so easy, you have to be a little more careful. And also one other thing, this omega y, as in all other previous examples of determining this new range, is that it has to be done on a case by case basis. There is no magic equation or formula that one can write down, except maybe here. Okay, so now having right said dealt with this issue of finding this range, let us look at how you might want to write the probabilistic description, the joint description of x and y. Here now what happens is the entire probability is concentrated on that curve as opposed to the earlier treatment of two joint x and y where you had a region of non-zero area. So, in this case remember that no matter what g is going up and down or not, or going monotonically, the entire probability is concentrated on the curve y equal to g of x. Now remember this being a function, the up and down is, it means that for a given value of x there is only one value of y, but for a given value of y there can be more than one value of x, right. That's understood by this. No matter what, right, which irrespective of the kind of g, the entire probability obviously cannot has to be only on this one curve. So, this means that the joint PDF is not the right thing to be looking for. You cannot write a joint PDF in such situations. The joint PDF can be written properly only if it exists, only if it can be defined over for a certain area, non-zero area. Curves always have zero area in the xy plane, right. So, joint PDF is not appropriate. This is not the appropriate tool for this situation. Okay, if that is not so, but it turns out that what you can do is treat y as a separately existing random variable and ask for the PDF of y separately, right. So that is what we will, that is the approach we are going to look at. We are not going to look at the right. Okay, one more point we can obviously say is, given that x is some, right, given that x has taken some value in its range, then there is no more randomness in y. You know exactly what is the value of y. Y has to take the value g of whatever, g of x naught what. So that so the conditional, if you look at it, the conditional PMF, so y becomes a deterministic quantity. So with probability 1 it will only take the value g of x naught when x takes the value x naught. So you also have that going for you in such a situation. So it is sufficient in this case to just to look at the standard PDF which we started looking at long back in this course. So it is sufficient to determine the PDF of y, determine, okay. Namely, now I am going to have to make a small distinction, y need, right, the discrete versus continuous. So what kind of a random variable is y going to be? So before we proceed with any calculations, we have to understand that. Right. So what kind of a random variable is y going to be? Supposing x is a discrete random variable, I think maybe I do not need this. Supposing x is discrete, which means that it can take only a countable set of values here, then y also has to be discrete. This is just due to the nature of the function g itself. Given that x equal to x1 or x equal to x2, y can only take a countable number of values, g of x1, g of x2 and so on. So in this case, right, we are going to say, so i.e. omega x, if omega x equal to some countable set like this, implies what? Omega y. Now of course some of these may be the same, g of x1 could be the same as g of x2, does not matter. If these are the same, then you have to recognize that and avoid replication, but that is besides the point. Let me, right, we can't, so we are assuming that these are all distinct, but they need not all be distinct, right. So in this in this discrete situation, it turns out that it is not worth spending too much time on this. Why is it not spending too much time on this? Because the PMF of y is, I think, extremely easily written down. You should be able to do it at this point. What is, for example, supposing the mapping is right, g is monotonic in that for x1 there is only one value, for any xi there is only one value g xi. So if what do you call such functions, one to one on the set, on this set, this is as a name for it, right, injective, surjective, one to one. I didn't document all those things anyway. So for anyway, one to one, supposing g for unique, let us say gxi, in the sense that this is gxi is not equal to g of xj for any I not equal to j, that is what I mean, right. If gxi is unique for all I, in other words, then p of y equal to gxi will be identical to what? P of x equal to xi. So this determines the PMF of y. If you do this for all I, automatically you generate the PMF of y. So this generates, but supposing you do not have unique gxi, supposing there are two numbers x1 and x2 let us say which map to the same gx1. Then what is that probability y equal to gx1? It will be the sum of the two numbers p of y x equal to x1 plus p of x equal to x2, because if you get either number in x, you are going to get the same number in y. Again, I am not going through write all of that down, or maybe I will write it down for the sake of the camera, right. I don't suppose, let us say gx1 is equal to gx2, then okay, right, x1. And how did we write this? We wrote this as small p of x1 plus this function px we used, right. So etc. So right, this procedure can be repeated as needed for all points in omega y. When once you repeat it or do it for all points in omega y, you generate the PMF. Remember, you have to do it for every single point in omega y, isn't it? You do not completely specify the PMF of a random variable till you nail down all the probabilities of all the points or values you can take, right. Okay. But I am assuming that, right, that is not a problem. So this discrete to discrete mapping through this function, although it's important in its own right, it is not considered to be sufficiently significant to devote a lot of space. So we will not come back to this anymore. You can do it by just common sense. The only thing I wish to emphasize is this kind of a calculation is basically is at the heart of what we are going to do in the continuous case also, and it is basically called conservation of probability. What does conservation of probability mean? That the unit probability in omega x somehow has to be translated to unit probability in omega y. So probability has to be conserved. You can't have a different overall probability here, right. This probability on this set must be identical to 1, the whole total probability. So you have this important principle of conservation of probability. Among all the other conservation laws, you have this one also. And this is not the first time we are seeing it. All the conditional PDFs, PMFs, everything that we wrote in the past week or so, every one of those has to be a valid PMF or PDF. That means it must have unit probability. Whether you write it as an unconditional PMF or a conditional PMF or a PDF does not matter. As long as you call it a PDF without any moniker, anything in front of it, it has to have unit area, unit sum. Right. So in so here also obviously you need to have, right, the same. So this means what, right? There is PY is a valid PMF.